If you've got aqueous problems, I've got aqueous solutions. Chapter 10. So we have talked about solubility qualitatively, meaning we're talking about it without numbers. Now we are going to talk about solubility quantitatively, with quantities, with numbers. So solubility of a compound is defined as the amount of the compound, typically in grams, that dissolves in a certain amount of liquid. It's basically always going to be grams, and then the certain amount of liquid could be in a couple of different units. For example, the solubility of sodium chloride at about room temperature is 36 grams. That's the sodium chloride per 100 grams of water. A solution that contains 36 grams of sodium chloride per 100 grams of water is a saturated sodium chloride solution. NaCl is sodium chloride. So a saturated solution holds the maximum amount of solute under the solution conditions, basically just temperature. You cannot fit any more of your solute, that's the minority component or the solid. You cannot fit any more of that into solution. It will not dissolve. If you add more, that's great. It's going to stay as a solid. It's not going into solution. It's not going to dissolve. So if additional solute's added, it will not dissolve. It'll just sit there at the bottom. You can try this if you want to, if you have extra salt lying around. This is something that you can do at home. You just dump a bunch of salt into like a clear glass, stir it around. If it all dissolves, add more salt, stir it around. If it dissolves, add more salt, stir it around. Eventually you'll just have salt floating around at the bottom, swirling. It's never going to dissolve unless you change the solution conditions. This is something that we utilize in lab if you need saturated sodium chloride. There are some instances where that's useful to have on hand. As long as you've got solid floating around the bottom, you know that your solution is saturated. Once you've started to use it up, if you need to fill it up, you just add more water, stir it around. If it all dissolves, you just add sodium chloride until it doesn't dissolve anymore. And now you know that you've got a saturated solution of sodium chloride. So this can be a helpful indicator in some cases. We've got some other options though. We also have an unsaturated solution. This is less than saturated, this un prefix of course meaning not. So it's a not saturated solution. That means that you can add more and it will dissolve. So if you add more, the solute will dissolve. The solute, again, being the solid, like the sodium chloride in the previous example. And you might think that those are the only two options. You would be wrong. We also have a supersaturated solution. If you compare a man versus Superman, is Superman just a man or is he more than a man? He's more than a man, right? He's actually not even a man, but based on the name, right? So a supersaturated solution is not just saturated, it's more than saturated. So a supersaturated solution, we've gone past the limits we thought were possible given solution conditions. So this is more than the normal maximum amount of solute. We have somehow sneakily snuck extra solute into our solution. Supersaturated solutions tend to be unstable. They will not just sit there and stay supersaturated. It will usually precipitate from a supersaturated solution or precipitate out of, often called crashing out. We've all been there. So it'll precipitate out of the supersaturated solution. They can form under specific circumstances depending on the type of solution that we have. So precipitate, here we're using the verb form. So it'll form a solid from the supersaturated solution. So if you leave a supersaturated solution sitting around and you come back later, there's a good chance that now you'll have solids sitting around even if it was previously all dissolved. Questions about any of our solutions? All right, let's talk about some ways that we can make saturated solutions. Here's some YouTube videos. Presumably the links work. In the past, when I've clicked on links in my slides, everything breaks, and so I don't click on links in my slides. I have a different setup now, so it probably wouldn't break, but it would be a little bit recursive to post YouTube videos on YouTube. But the general idea is supersaturated solutions are unstable. So this is a solution that was supersaturated. Because it was supersaturated, there was more than was supposed to be in there. It started to crash out, it started to come out, it started to precipitate and form these crystals. And some solutions form really sharp, jagged crystals, which is kind of cool. They look neat. And sometimes they'll form almost instantaneously, so that's what these sodium acetate solution videos are. I'm pretty sure one of them, they just touch the surface and immediately the whole thing basically turns into what looks like a block of ice. So that's kind of nifty. The way that we can produce a supersaturated solution is by varying temperature, at least for solids. So on this slide, we're talking about the solubility of solids, solubility versus temperature. So generally, the solubility of solids in water increases with increasing temperature. This is probably something that most of us know, even if we didn't know that we knew it. If you try to dissolve sugar into hot tea, it's going to dissolve a lot more easily than iced tea. If you try to dissolve it into iced tea, it's going to take forever. It will still dissolve. You won't be able to get as much in, but it will dissolve eventually. Hot tea, it's in right away. So if you're making simple syrup for a mocktail or something, you're probably going to make it with hot water because the sugar will go in immediately or near immediately. The temperature dependence of solubility varies, but there's a general trend, and that's that it increases with temperature. So in our graph, we've got solubility curves. We've got a bunch of different chemicals here. On our x-axis, we have temperature. So as we're moving left to right, we're increasing temperature. And on the y-axis, we've got the grams of solute per 100 grams of H2O. So that's our solubility. So as we're going up, that means that we're increasing our solubility. So generally, if we look at these things, right? We pick a line. We follow this KClO3 line, the fuchsia line. It starts out pretty low on the left side. As we move to the right, as we increase temperature, we can see our solubility going up. They have different shapes. Some of them curve up. Some of them sort of curve down. Some of them stay relatively flat and move in straight lines. And SO2, which I think should be a gas, goes down. Questions about solubility of solids? So generally, as we increase temperature, solubility goes up. We can use that trend to do things like recrystallization. Recrystallization is what we did in our alum lab, but we did a really fast version, so we didn't get very good crystals. If you saw the little thing of crystals that I was walking around, that's a better example of recrystallization. Bigger crystals, nice and pure looking. So recrystallization, the re part meaning again, crystallization, we're forming crystals. So forming crystals again from our solid is a common way that we can purify some solids. So the way that we do this is we make a saturated solution at an elevated temperature. As the solution cools, the solubility decreases, and this causes some of the solid to precipitate it. It comes out of the solution. If you cool it slowly enough, it'll form crystals as it comes out. It takes time for the solution, for the solute, to stack all of those little ions or solids on top of each other. It has to build out in a nice, even manner to make a crystalline structure, and that takes time. Rome wasn't built in a day, and your solids aren't crystallized super fast either. When it does this, that crystalline structure tends to reject impurities because they stack so nicely on top of each other. Other things will often get kicked out, and that can result in a purer solid. So let's look at the graph to see what we were talking about here. So we're going to make, let's take this KNO3, for example. this red dot. So we make a solution at elevated temperature. So at this temperature, this 65 degrees Celsius or so, we've got 120 grams per 100 grams of H2O. That's a lot. We prepare our solution at this temperature, and then we decrease the temperature. So we're moving from the right to the left. We decrease the temperature, and that causes our solubility to plummet. But we already have this amount of solution, or this amount of solute in our solution. So now if we come back, if we back it off to say 30 degrees Celsius, to our cooled solution, the solution wants to stay on this line in terms of its solubility, but we're way up here, and so that solubility is going to crash. So our solubility comes down, and that's going to cause things to crash out, 70 grams or so that we lose in terms of solubility capacity. Questions about any of that? Cool. This is also something that you can do at home. I encourage you even to do it at home. I have yet to get somebody sending me pictures of, hey, I did that thing at home from class. I would love for somebody to send pictures of making rock candy. So recrystallization is a way that you can make rock candy at home. You don't have to go out and buy it. If you want it to have color to it, you might have to add some, red 40 or some other sort of food dye to it. The way that you make rock candy is you prepare a saturated sucrose table sugar solution at elevated temperature. So you can get some really hot water, maybe up to like 90 degrees Celsius, almost boiling. You could probably do it with boiling temperature water. You're going to dump as much sugar as you possibly can into that until you've got some solid swirling around at the bottom. Then you dump out your super sweet sugar solution into a container. Either like, if you pour it into glass, you probably want to make sure that the glass has been heated up first, but you could put it into something like an old hydro flask, because hydro flasks are not in right now, but you probably have one lying around. Pour it into a hydro flask because those are insulated. That's going to keep the temperature from plummeting. Pour it in there, run a little string through the top, close the lid, and just leave it until it cools down. It might take a while, could take a couple days. That string is going to have lots of rough spots on it. If you remember our alum lab, I believe in our alum lab, I had you scratch the surface of the glass. That was to create rough spots. That gives the sugar, or the alum in our case, in that lab, it gives it a place to start to settle in. If you've got a completely smooth surface, there's nowhere really to latch on. So it gives it a little bit of a hold to start making the crystals. Your string is going to have lots of jagged spots all across it. So that's going to be probably where it is going to want to form these sugar crystals. If you let it stand for a while, once it cools down, it should become super saturated, and you'll get sugar crystals growing out. And then you've got a nice crunchy sugar treat. So please, somebody try this at home and report back. It's also the sort of thing that you might be able to like make flavored rock candy. There's probably videos on YouTube. So that's a thing that you can do. So that's solids, solutions of solids in water. There's also solutions of gases in water. So a can of soda is a great example of a solution where a gas, in this case carbon dioxide, is dissolved into liquid water. Most liquids, if they're exposed to air, contain some dissolved gases. If you have ever had well water, this is probably especially true. My experience with well water is that it's usually very bubbly. But maybe this is not all wells. Hashtag not all wells. So most liquids are going to contain some dissolved gases. Usually you don't see them. Usually you don't notice them. They have to be there for animals to survive. So you might know that fish also breathe oxygen. Fish need oxygen to breathe. That's why most fish tanks have the little waterfall bubbler, or they've got a little thing that bubbles through the water. If you don't do that, there's only so much oxygen in the water. You might notice your fish coming up to the surface to get a breath of air, to get some dissolved oxygen. Or maybe you just don't have fish anymore. It's important to have a bubbler so that your fish can breathe. Our blood also contains dissolved stuff like nitrogen, oxygen, and carbon dioxide, and even tap water contains dissolved atmospheric gases. So how does solubility of gases change with temperature? Solubility of gases versus temperature. The solubility of gases and liquids decreases. It goes down as you increase temperature. So this is another that you could try at home if you take a warm soda and if you take a really cold soda and you open both of them, and you take a sip, you'll probably notice the warm soda feels a lot fizzier. It's a lot more aggressive on your tongue than the cold soda. It's probably also going to do a lot more whooshing as you open the can because of that change in solubility. Carbon dioxide gas is going to have decreased solubility at high temperatures. So that means you're going to have less carbon dioxide in your water, and so more of it's going to be released. You could also, like, if you have ever squeezed like a really cold can of soda, it has a lot of give to it, and a warm can of soda doesn't have very much give to it. Another way that you can feel that difference. Okay, so looking at the solubility graph, we've got temperature on our x-axis. Lower temperatures this time. We've got increasing temperature left to right, and we've got solubility just with different units on our y-axis. So higher up means that we've got higher solubility, we can get more dissolved into solution. Lower means lower solubility. And we can see that for all of these gases, our trend is that as we increase temperature, we decrease our solubility. So this is opposite for our solids. So increasing temperature decreases gas solubility. And again, this is opposite of solids. Questions about the temperature dependence of solubility for gases? Okay. Gases also, their solubility also depends on pressure. And so we've got, for this, Henry's law. Henry's law states that the higher the pressure of a gas above a liquid, the more soluble the gas is in the liquid. So we've got two different states here. We've got a movable piston in a cylinder. We've got our liquid on the left. We can see there's some dots that's representing dissolved particles. We've got a bunch of dots up in the air portion. If we push that cylinder, that piston down, that's going to increase the pressure of our gas. Right? We've shrunk the amount of space that that gas has to occupy. That's going to increase the number of collisions. And that's going to cause some of these to escape into the liquid. And so that's why we see an increase in the number of particles that are in the liquid. So higher pressure forces more gas into solution. It forces it to dissolve. Gets pushed into the water. And this is how cans of soda stay pressurized. So a can of soda is pressurized with carbon dioxide. I believe it's about 2 atmospheres of pressure. So when you open the can, you hear that whoosh because there's extra pressure that's being let out. And when that pressure is released, that lowers the solubility of the carbon dioxide in the solution, and so the carbon dioxide starts to bubble out. If you just leave a can of soda out at atmospheric pressure, it will eventually go flat even if it's like in your fridge. It just goes flat over time because the solubility is going to lower so that it's no longer fizzy. Questions about Henry's law? All right, I'm going to draw, risky I know. Fortunately, it's a graph. And this is a graph that we've seen before. I'm going to graph it as temperature instead of energy. Energy and temperature kind of go hand in hand. If we were to map our states of matter onto a temperature graph, what's going to be our lowest temperature phase of matter? Solid. Right? Like ice. Solid is going to be our lowest temperature. What's going to be higher temperature above solid? If you increase the temperature of a solid, what happens eventually? It turns into a liquid. And then if you keep heating up your liquid, what will it eventually turn into? Gas. All right, thinking about solids, when we increase the temperature of a solid, does it become more or less like a liquid? If we increase the temperature, we're moving, for our solid, we're moving up on this graph, right? It's going to become closer to being a liquid. So as temperature increases, solid becomes more like a liquid. As the temperature increases, the solubility of solids also increases because it's becoming more like a liquid. How would we make a gas more like a liquid with temperature? Are we going to increase temperature or decrease temperature? Decrease temperature. So if we decrease the temperature of a gas, the gas becomes more like a liquid, and so its solubility increases. And the opposite is also true. If we have a gas and we increase its temperature, we'll do this in blue. If we increase the temperature of our gas, we're moving away from it being like a liquid, and its solubility is going to decrease. It doesn't get along because it's now more gas-like and less liquid-like. So I think that this is a fun graph for showing that the way that we think about the solubility is how do we get this state of matter to become more like a liquid. The more that it's like a liquid, the more it's going to dissolve. So I think that's neat. You don't necessarily have to use this. You could also just memorize the way that solubility of gases and solids changes. Okay, now to the quantitative part. So fly or something. Mass percent. Mass percent is the number of grams of solute. Grams of solute per 100 grams of solution. Per here means not the sound a cat makes, divided by. So grams of solute divided by 100 grams of solution. Shoo fly, don't bother me. A solution with a concentration of 14% by mass contains 14 grams of solute per 100 grams of solution. The solution is solute, possibly more than one solute, and solvent. The solvent is the majority component, or the liquid, and the solute or solutes are the minority component, or the not a liquid. So our formula for mass percent is given here. Mass percent equals the mass of the solute divided by the mass of the solute plus the mass of the solvent. That's the mass of the solution. And then because it's a percent, we multiply by 100%. Questions about this formula? Generally, we're not going to need to separate out mass solute plus mass solvent. Sometimes it'll be helpful to have those separated. Okay, an example using mass percent. Calculate the mass percent of a salt solution containing 12.8 grams of sodium chloride, 357.1 milliliters of water, and we can assume that the density of water is 1 gram per milliliter. This 1 gram per milliliter means that we can just convert the milliliters into grams. If we want to be rigorous about it, 357.1 milliliters of water. Our density has grams over milliliters, so we'd multiply by grams per milliliter. Milliliters cancel, and we can see that it's the same number, just with different units. One of the convenient things about water. All right, so we are trying to get to mass percent of the salt solution, so we need to use our formula. Mass percent equals mass solute over mass solution times 100%. We have the mass of the solute. It's this 12.8 grams. We don't have the mass of the solution. This is an instance where it would be helpful to write it instead as mass solute plus mass solution. Because we have the mass of the solute, we have the mass of the solvent. That's what I meant to write, not solution. Okay, now it's correct. So plugging in our numbers, the mass of the solute is the 12.8 grams sodium chloride over the mass of the solute. We determined that that was, nope, the other one. The solvent is the 357.1 grams. It doesn't matter what order they're in, by the way. And then times 100%. Please pull out your calculator. Put that into your calculator. And see what answer you get. Okay, the place where we can go wrong with this is if you either don't add the things on the bottom first, or, yeah, that's basically it, because parentheses would tell your calculator to add the things on the bottom first. You have to have parentheses under the things on the bottom, or you add them first, and then do your division and multiplication. Done correctly, this should give you an answer of 3.46% sodium chloride. If you did it wrong, it's something like 35,700% sodium chloride, which hopefully sets off alarm bells in your head, because this should never be a number above 100%. Okay, there are also some other commonly used units that you might see if you are for some reason looking at your local county water report, like one does. I've done it many times. Parts per 100. Parts per 100 is the same as percent. There's also parts per million, ppm, which is more like what you would see on like a pesticide residue label, or there's like amounts that you're allowed to be exposed to before it starts to harm you. Those will often be maybe with ppm. It's the number of grams per 1 million grams. So 1 gram per 1 million grams, usually parts per million is in terms of mass. There's also parts per billion, ppb, and that's grams per 1 billion grams. There's also ppt, which is parts per trillion. Those are typically numbers that you'll see for, like, this is the amount of microplastics that we found in people's brains, or other such fun things like that. So if you see those, congratulations, now you've seen them before and it won't be your first time. You'll be like, hey, I recognize that. And then you'll be like, what was that again? Or you'll just say, ah, that's a number. We can also use mass percent in calculations, so oftentimes you might be given mass percent. The key to using mass percent as a conversion factor is to write it as a fraction. So mass percent equals the number of grams of solute per 100 grams of solution. For example, if you have a 34% something, you can rewrite that as 34 grams of the solute over 100 grams of the solution. And this is one of my least favorite parts of the entire class to explain, because my brain just, I've been doing it for so long that my brain just does it automatically. So if you're feeling left behind, go to SI sessions, and Logan would be happy to explain it to you, or give you some practice problems. Okay, how much sucrose in grams, sucrose in grams is contained in 355 milliliters of a soft drink containing 11.5% sucrose? Assume the density is 1.04 grams per milliliter. So it's no longer 1 gram per milliliter. We can't just change out grams and milliliters. We do actually have to do a calculation. Okay, so density equals mass over volume. We can use that here. We are looking for the mass. Since we did it the dimensional analysis way, we'll do it the algebra way this time. So we start with D equals M over V, multiply both sides by V, and mass is equal to volume times density. So 355 is our volume. We're going to multiply that by our density. Look at that. It's the same solution. So 355 times 1.04, we get 369.2. And we'll retain 3 significant figures. So that's grams, but grams of what? Solute, solvent, solution. Which one of those 3? Yeah, it's of a solution. So grams solution. And we were also given this 11.5% sucrose. So 11.5% sucrose, we can rewrite that as 11.5 grams of sucrose per 100 grams solution. If you're so inclined, you can also just simplify this. 0.115 grams sucrose over 1 gram solution. Those are exactly the same thing. You can use either one of them. My brain likes to just turn the percent into the fraction, the decimal form, and then multiply that way. It doesn't matter. It's the same outcome. Okay, so we're taking our grams of solution. We're going to multiply by either one of these, grams of sucrose over grams solution. So 369.2 grams solution multiplied by 11.5 grams sucrose over 100 grams solution equals, grams of solution cancel out, and we get 42.5 grams sucrose for our answer. There. That. It's not a drive-by, it's a flyby by a fly. Just tapping me on the forehead. I'm probably on a dream. There is another way that we can do this if you've got the mass percent formula. You can also plug in mass percent, that's the 11.5%, and the grams of solution to find the grams of solute. You can also do it that way. It'll get you the same answer as long as you don't get your orders of operation out of order. Questions about all the fun that we're having? Okay. Now we are going to learn a new unit. This new unit is called molarity. We've seen molarity before. It's shown up in our lab many times, lots of solutions with some number and then big capital M. So molarity, capital M, big M, majuscule M, uppercase M. It's important that it's the big one, is defined as the number of moles of solute per liter of solution. So we've got this lovely formula. And we're pointing out here that it's liters of solution, not solvent. So remember, the solution is solute plus solvent. So that's the whole thing, all the liquid with everything that's dissolved inside of it, which is way more convenient than if we try to figure out just the amount of liquid and not the amount of stuff that's dissolved into it, because the amount of stuff dissolved changes the volume a little bit. So it's better this way. This is another equation that we can use, that little triangle method thing that we used with density. Some people like to use this. So if we make a little triangle, we can put molarity in the bottom left, we put moles in the top, we put liters in the bottom right. Whichever one you're trying to find of these three, let's say we're trying to find moles. Moles equals, let's look at how the other two things are related. Capital M is next to L, so molarity times liters. So you just cover up the one that you want to find, which I can't do because it's a projector, but we'll do it anyway. Boom, moles it's on my hand. Moles, cover that one up, big M times big L, and now you've got moles. That's the way that you would do the calculation. Same idea for finding the other two. So for liters, you take moles over molarity. And that gives you your liters. It works. Or you can just use the formula and rearrange it. Okay, if we want to make a solution of a specified molarity, here's what that would look like. Diagrams. So we're going to take our solid, we're going to weigh it out. We'll take a volumetric flask because we care about volume accuracy. We're going to have a little bit of liquid in there. We add our solid into the liquid. Volumetric flasks get really skinny at the top and they're bulbous and round at the bottom. It'll mix well if you've got some air in the bottom part. So we're going to dump it in, then we'll shake it around to get everything dissolved, and then we'll fill it up with water to the fill line. Volumetric flasks are only good for measuring one volume, so we're going to fill it up to the line, so the meniscus, the bottom of the line, the meniscus is on the line. And then, kablamo, we've got our solution made. I don't know that you'll ever do this, but that's how you're supposed to do it. Hopefully, if you ever make the mistake of filling up the liquid above the big bulbous bottom part, that's probably a mistake that you hopefully only make once, because you fill it up and you're like, now how do I shake this thing? Because it's a nightmare to shake to get it to swirl around when it's basically full. Let's do a calculation. So for calculating molarity, we want to calculate the molarity made by putting 22.4 grams HCl into a beaker and diluting to a volume of 1.56 liters. Our formula, our equation, molarity equals moles over liters. Do we have liters? Yes, we have liters. It's 1.56 liters. Do we have moles? No, we don't have moles. How do we get moles? We convert grams to moles. So we're going to have to take our 22.4 grams HCl and convert it to moles of HCl. What do we use to convert grams and moles? Molar mass. Do we have a molar mass for HCl? We don't. So we need molar mass of HCl. Lucky for us, we're all pros and we've been staying up to date. We've been keeping up our skills with finding molar masses, so we just simply pull out our handy dandy yellow sheet. We find H, there's one H. There's also one Cl. H is 1.008 grams per mole. Cl is 35.45 grams per mole. That's all that's in HCl. So we add them up and we get 36.458 grams per mole. How do we use this to convert? Are we going to multiply or divide? We're going to divide, so the 36 grams goes on the bottom. And the 1 mole flips to the top. We'll add the HCl labels on there. So we've got grams HCl to start, so we put the grams HCl on the bottom so that they will cancel out. And they do. And what's left over is moles HCl, which is what we wanted. So 22.4 divided by our molar mass, 0.614 ... moles HCl with 3 sig figs. Now that we have moles and we have liters, we can calculate our molarity. So big M, capital M, molarity equals 0.614 ... because there's other stuff and we're going to use it, divided by 1.56 liters equals. And then we take that 0.614405617 and we divide it by 1.56. Round it to 3 sig figs, we get 0.394 capital M HCl. Any questions? So we can calculate a molarity. We can also use it as a conversion factor between moles of solute and liters of solution. So capital M equals moles over liters. And there's a fun thing that we can do thanks to math. So anytime that you see capital M, you can substitute in moles over liters. Every time. I like to take advantage of that. I'm a big fan of dimensional analysis, using our units to solve our problems. So for example, we want to determine grams of sucrose in 1.95 liters of 0.781 molar sucrose solution. I'm going to sub in moles over liters for this capital M. This does a couple of things. One thing that it does is it shows us that this capital M is not actually just one unit, it's 2 units in a trench coat. Right? It's moles over liters, they've stacked up. Even though we write it as capital M, it's secretly 2 units. Since there's 2 units in there and one's on top, the other's on bottom, that means it's a conversion factor. So I'm generally not going to start problems with capital M. Liters is just 1 unit. So I will usually start with liters. So 1.95 liters of the sucrose solution times 0.781 moles. The liters gets kicked to the bottom, so the liters cancel. This tells us, without doing any algebra, it tells us that we multiply these and the liters will cancel out, and that will give us moles. You could also use this big M equals moles over liters and solve for moles. If you do that, you'll get moles equals molarity times liters, which is what we did here. Questions about that part of it? We can sub in moles over liters for capital M, anywhere that you see it. It's one of my favorite tricks. So we would get this out for our number of moles of sucrose, which is C12H22O11. We would multiply by our molar mass, which I don't have, so we'll have to calculate it real quick. (342.297). Multiply those that seems too high. Oh well, maybe it is that big. 521 grams of sugar. That's a lot of sugar. Sweet. So at this point in the class, it's just kind of assumed that you can calculate molar masses given a formula. It's also assumed that you can come up with a formula given a name. So those things will probably show up on the final. Sometimes I will be nice though, like if I give you a question like this, I might be nice and just give you the molar mass of sucrose to save you time and brain power. All right, one for you to try. How many liters of a 2.25 molar copper sulfate solution, copper 2 sulfate solution, contains 55.8 grams of CuSO4? And since we just encountered it for the first time today, molarity equals moles over liters. And I'll give you some time to give that a try. If you're stuck on the molar mass, go to Logan's SI session. But I'll also just give you the molar mass. We've got 1 copper, we've got a sulfur, we've got 4 oxygens, I'm going to add all of those up. I had my calculator in my hand, that's why I couldn't find it. Molar mass is 159.606 grams per mole. Okay. We're finding what? Liters. We're looking for an answer in liters. We were given 2 things. We were given a concentration, 2.25 molar copper sulfate solution. This contains 55.8 grams of CuSO4, which has this molar mass. Which one are we going to start with? Are we going to start with grams or molarity? We should start with grams because molarity is secretly moles per liter. Grams is a singular unit. So 55.8 grams CuSO4. And our goal is to get to liters. To get liters, we would need the other 2 things. We would need moles, we would need molarity. We have molarity. We don't have moles, but we can use grams to get to moles. Are we going to multiply or divide by our molar mass? It's hopefully something that you either didn't ask yourself because you just knew what it was, or something that you did ask yourself because you wanted to make sure you did it correctly. And we are going to divide so that the grams part is on the bottom, which means it will cancel out the unit that we have. The unit that we want, which is the moles, will go on the top. Okay, so grams, CuSO4. And now we can calculate our moles. It's 0.349 ... moles copper sulfate. Now, molarity is moles over liters. So the way that I would solve this problem is I would sub in moles and liters. We are trying to get liters, so we'll need to flip this. Flip. Liters over 2.25 moles. Now liters is on the top. We multiply our moles, and boom, bam, bop, we got the right answer. Or, if we're solving for liters from molarity equals moles over liters, if we multiply both sides by liters, this turns into liters times moles. Sorry, molarity equals moles. We divide both sides then by molarity. And this turns into liters equals moles over molarity. That's the way the algebra works. This would be the same as taking our molarity, flipping it, so it's 1 over m, look at that, and multiplying it by our moles. It's the same outcome, just a different route to get there. Okay. Over 2.25 moles per liter. Liters flips to the top, moles gets canceled out. And the number of liters, 0.155 liters. Questions? Confusions? Any, Mr. K, how did you do that? Mr. K, why did you do that? Yeah.
Can you explain how when you flip it, like if you flip the moles over liters, how that would be like algebraically equivalent to the second part? Because I understand that. Like
This part?
Yeah.
Flip. So this is molar. If we flip it, it's m to the negative 1, or 1 over m. And so then if we multiply this by moles, the moles is up on top and the molarity is on the bottom. So that's how it would end up working the same. Other question?
Why would you do all that instead of just using the triangle from earlier? Like, is there a difference?
You can just use the triangle from earlier. Lots of people prefer that. Yeah, it works for this type of equation. It's not something that I've been familiar with for a long time, so I typically don't use it. But yes, it works and it simplifies things for lots of people, so you're welcome to use it. Encouraged even. Okay. Other stuff that we can do. When we've got solutions, sometimes we've got ions. Those ions have concentrations in our solutions. The reported concentration, like 2.25 molar copper sulfate, the reported concentration of a molecular solute usually reflects the concentration of the solute as it exists in solution. So 2 molar sucrose means 2 moles sucrose per liter of solution. The number means what it says. The reported concentration of an ionic solute reflects the concentration before it is dissolved in solution. For example, if we've got a 1 molar calcium chloride solution, that's going to contain 1 mole of calcium chloride per liter of solution. Calcium chloride, though, has 1 calcium, it has 2 chlorides, and so it's going to have 1 mole of calcium per liter and 2 moles of chloride per liter. The 2 moles of chloride, because you've got 2 chlorides per 1 calcium chloride. Two Cl per 1 CaCl2. So if we're starting with 1 molar CaCl2, calcium chlorides cancel, it should have a minus, will be 2.0 molar Cl minus. So it's sort of like we're doing a little bit of stoichiometry, but it's like the light version, LITE, light version. If we want to calculate some ion concentrations, let's determine molar concentrations, molar being capital M, concentrations of calcium and chloride in a 1.25 molar calcium chloride solution. So we've got 1.25 molar CaCl2 on the top. Let's calculate for calcium. On the bottom, we'll calculate for chloride. How many calciums do we have in a calcium chloride? It is 1 for our one guesser. So 1 calcium 2 plus in 1 CaCl2. We know that there's 1 because there's no subscript. No subscript means that it's an implied 1. So calcium chloride parts cancel out, and our concentration is just going to be 1.25 molar calcium 2 plus. We can do the same thing, but for the chloride ion. How many chlorines do we have in a CaCl2? It's 2. 2 Cl minus for every 1 CaCl2. And since we've got 2 per CaCl2, that means that our concentration is going to be twice the concentration of our CaCl2. So it's 2.50 molar Cl minus. If you want to on these, if it helps, you can always write out an equation for what it will do when it dissolves. So CaCl2, when that dissolves, it's going to break into its ions. There's going to be Ca2 plus. There's also going to be 2 Cl minus. And then you can use the ratios to figure out your conversion factors here. And next class, we'll learn about a very helpful but troublesome equation for solution dilution.